So last day we ended by talking about solving a system. Now that I've written it in this form, let's make a couple of assumptions, okay? A is n by n non-singular. That means that A inverse exists. It also means that A is invertible. So invertible and non-singular go hand in hand. Okay? Non-singular is a very mathy word, right? You say, what does it mean? Well, it just means it's invertible. That's more of a description. But non-singular actually comes from something else. Somebody asked about determinants the other day. It really comes from that. So A is n by n non-singular, which means A inverse exists. Therefore, X will equal A inverse times B. Now notice, this is very important. Matrix multiplication is not commutative. So I would have to multiply both quantities on the left by A inverse. I can't just arbitrarily multiply it on either side. You see, A inverse on the left is legal. But if I tried to put A inverse on the right, this is n by 1. I can't multiply on the right by n by n, can I? That won't work. I have to multiply on the left by n by n. Okay? So we're going to do a problem from beginning to end where we're going to solve it using the inverse. Not that it's more practical, but it's just very useful to have options because sometimes this is how we will solve things. And this is one of the rare areas where technology can help us. We don't need technology if it's 2 equations or 3 equations. What if it's 10 equations? You know, what if it's a huge problem? I don't want to sit there and do it by hand. I want to know what is the mathematics required to do it by hand, and then I have the computer do it. Does that make sense? When it's small, you don't need technology because you can get it done fast enough. I laugh when people will use technology to do really, really short processes. I said, it took you longer to enter it into your calculator than it would have if you just do it. But it's good to know both. Okay, so let's start with a simple problem. Let's say, well, here's our problem. And I'll make it easier to start with. x1 minus 3x2 plus 4x3 equals, let's see, let me make this simple, 7. Negative 2x2 plus, how about 4, x1 plus 4x2 minus x3 equals negative 3, and 3x1 minus x2 plus 5x3, again. Oh, I gotta tweak this one. Okay, sorry, I just want to make sure, I tried to reverse engineer it so it'll actually come out, you know, less hateful. No, we have no idea what the nature of the solution is, but I know because I can look at the numbers and see a little past it. I'm playing chess and I'm moving 2, 3 moves ahead because you don't know how to yet. In a really short time, you will actually be able to look at that and tell me, yes, there is a unique solution. I can change one number in this to make it so there's not a unique solution. But this will have a unique solution. Okay, everybody cool with that? I think this will have a unique solution. Let's see. Yeah, this will definitely have a unique solution. Well, let's see. I'm going to change one thing just to make sure. I'm going to change this 5. Sorry about that. I'm going to change this 5 to a 3 and make this a 10. I saw too many similarities. We want to set up the matrix problem that we're going to solve to get the solution, which means we're not going to augment it with these numbers. So we're going to start with the coefficient matrix. I'm hoping the numbers come out well. You know, I'm doing this in my head sometimes. Now, we're not going to augment it with the numbers on the right. We're going to augment this with the identity matrix. This is the process for doing an inverse in general. I did it last day with a 2 by 2 and showed you 2 by 2s have a tremendous shortcut. If I give you any 2 by 2 matrix that has an inverse, you can tell me the inverse literally in seconds. There's so little to do. It's awesome. It's wonderful. But that shortcut doesn't apply to 3 by 3 or bigger. There are versions that apply, but not the same way. So what we're going to do then is do 1, 0, 0, 0, 1, 0, 0, 0, 1. Now here's our strategy. We're not looking at anything on the right. We're going to manipulate the left side and do row operations until the left side is the identity matrix. Okay? If my original matrix is row equivalent to the identity, then my identity would be row equivalent to the inverse. If this matrix is not invertible, then I cannot make the left side ever look like the identity, which means that I'd never make the right side look like the inverse because it wouldn't exist. So I've got to make that the identity, and these are just going to follow along. Whatever I do here, right, it will just carry through. So the process itself is not short and sweet, and I really want to avoid fractions as long as I can. Now understand that if everybody here, heck, let's just make up 2 by 2s. Everybody here make up 10 2 by 2s. There's 30 of you in here, that's 300 matrices. Great. Now find the inverse. How many of your inverses will have all integers of the 300 you suppose? Well, first of all, a good answer would be not very many. I don't know, maybe 5, 10. No, they'll all have fractions. You have to really work hard to make it so that all the values are integers. Don't look for integers. Now, what you are going to have is all rational numbers. You're not going to see square roots. You're going to see fractions. I mean, you can live with fractions. But what you want to do is avoid introducing them as long as you can, because then you have to manipulate them all the way through the problem. Well, I have a pivot of 1. Can't get better than that. So how about 2 row 1s plus row 2 to start? So 1, negative 3, 4, 1, 0, 0. Then 0, 2 of those, that'd be negative 6 plus 4. 2 of those, that'd be 8 minus 1. 2 of those. And now how about negative 3 row 1s plus row 3? 0, negative 3 of these, that'd be 9 minus 1 is 8. Negative 3 of these, that'd be negative 12 plus 3 is negative 9. Negative 3 of these. Okay. Now that pivot is great for the one below it, not so great for the one above it. Now, I have 2 choices here. I can leave it as a negative 2, but at the end of the problem, by the time we're done, that has to be a 1, doesn't it? This has got to be 1, 1, 1 with all zeros. So at some point, I'm going to have to take negative a half. I can do it right now and just suck it up and deal with the halves. Or I can multiply the top row by 2 and make it a multiple of my pivot. But then somewhere down the road, I got to change it back to a 1. Both are legal, both are correct. If you don't mind working with halves, because halves are not evil. 37 is a denominator, that's evil. But 2, I could probably live with 2. So I'm going to go ahead and multiply by negative a half. Okay? You actually have a choice there how you want to work with this. Because it's perfect for the one below, like I said, but not for the one above. So 0, 1, negative 7 halves, negative 1, negative 1 half, 0. I haven't done anything to these guys yet. Okay. Now I will use my pivot of 1 above and below. So 3 row 2s plus row 1. Okay, so 1, 0. Negative 21 halves plus 8 halves, that'd be negative 13 halves. Negative 3 plus 1. Negative 3 halves plus 0, 0. Okay? This way, negative 8 row 2s plus row 3. So 0, 0. Negative 8, so it'd be positive 56 halves, or 28 minus 9 would be 19. Negative 8 plus negative 3, that'd be negative 11. Positive 4 plus 0. 0 plus 1. Okay? We're almost there. And I have a lovely pivot of 19. Big yikes. So if I've made no error, I hope I haven't made a mistake. If I've made a mistake and you haven't pointed it out, shame on you. Now, do you want to make these multiples of 19, or do you want to make that a 1? Doesn't matter. Which way do you want to go? You have a calculator in your hand for fractional stuff, just so you know. Well, we're this far. Let's go ahead and make it a 1. So 1/19th, row 1. Or, row 3. All right. Now, go ahead and get out your calculator and use the fraction key on it. You do not want decimal approximations of rational numbers if they're not terminating decimals. And I don't think you're going to get a lot of terminating decimals with these values. Okay? So we're going to do 13 halves row 3 plus row 1, and we're going to do 7 halves row 3 plus row 2. All right? I would like you to do this on your own. I'll start you. Use the calculator. Now, here's what I do know. I'm definitely going to have that. So now I'm going to take 7 halves times negative 11/19, and I'm going to add it to negative 2. Yikes. You with me on that one? Use the calculator. Use the fraction key. Okay? Anything else would be kind of silly.
I think we made a mistake.
Oh, where?
When we did negative 8R2 plus R3, the fourth one should be a 5.
The fourth one.
Sorry, the negative 11 should be a 5.
What do I think? Oh, okay, so negative 8 of these would be 8 plus, thank you. I wish it was the 19 that was a mistake, but that should be a 5. So that should be a 5/19. Great call. Oh, yeah, we would have had an error and we would have never been able to figure out what it was because it wouldn't have worked. But I'm showing you, by the way, I'm going to show you every conceivable check there is. But there's no check yet. We have to actually have an inverse first. Yeah, you're definitely correct. So negative 8 of those, I think those numbers are correct, right? Yeah, those are good. Okay, so I'm going to leave this to you guys to do just for a moment. It's not necessarily pretty.
How do I keep a fraction load on a calculator?
On your calculator, do you have a fraction key? It should look something like that one.
Okay.
Yeah, the problem with a lot of the big fancy graphing calculators, your fraction key might not be a main key. And that makes things really, really impractical. Does anybody have a graphing calculator with a fraction key on the front?
Yeah.
Where's your fraction key?
I like calculator here.
Okay, good. Yeah, that in this course, that may be the key you use the most often because you're going to work with matrices. This step right here is a perfect example. I need to take 7 halves of this and add it to that. I need to take 13 halves of this and add to that. I don't want to do that pencil and paper. Are you crazy? It takes forever. No, just quickly use the calculator. So, 5/19 times 13 halves minus 2. So what do you get here? I get negative 11 over 38. Anybody else get that?
Okay.
Oh, good. Okay. That means we're on the right track. And then 4/19 times 13 halves. And that would be then what? Let me replace that. And I'm adding it to negative 3 halves. And I got negative 5/38. And then 13, I can just do that in my head, that'd be 13/38. All right, anybody else get that? We're all on the same page? All right, then the next row, oh, by the way, I don't need to do anything here, so this is already 5/19. Well, actually, I'm gonna hold off. I'm gonna hold off on that one. Because I'm gonna do something different here. All right, so 7 halves. So 5/19. And adding to -1. So -3/38. And then 4/19 times 7 halves minus 1/2. 9/38. And then 7/38. Okay, do we all agree so far? If you got a different number, please don't. If we all agree, then we're either all right or all wrong. Again, use the fraction key on the calculator. Now, last row. Do I want 5/19, 4/19, and 1/19? No. That's the one thing you never want. This is a never with like 3 more nevers following it. You never want a matrix with fractions with different denominators. That makes things so much more extra work. No, make your denominators 38. Because when you go to check it and you go to multiply, having different denominators just means one more thing you're going to have to do. It's unnecessary. I'm going to make my denominator 10/38, 8/38, 2/38. Okay? Is it correct to reduce fractions in a? Yes. But if it produces different denominators, then it's not necessarily a great move. I'll give you a simple example. Let's say hypothetically, I have a row, and my row is 3/12, 4/12, 6/12. That's my row. So you're going, I'm going to be really clever and reduce that to 1/4, 1/3, and 1/2. You would be correct, and you just made this problem 10 times harder, because now you've got to use different denominators in every, which means you then have to change everything down the road. I don't want to change anything down the road. No, I would leave it like this. Now, what if these were all, what if this was 110/38 and 50, or I'm sorry, 110/380 and 50/380? What if every one of these numbers had an extra 0 on top and on bottom? Yeah, I'd probably catch the zeros.
Does that mean the determinant is 38?
Could be. Could mean. Or -38. We're getting a little ahead of ourselves, but you're correct. That 38 has something to do with the determinant when we get there. But we're not going to get there for a few days. But yes, that has something to do with it. It absolutely has something to do with it. Now, I'm pretty sure I did this right. Okay? What is my coefficient matrix? I'm going to write it down. My coefficient matrix is this. Okay? My matrix equation is this. I want to show you this is what we're actually doing in this problem. I haven't made any mistakes. So this is the matrix equation. Okay? This is the coefficient matrix. So at some point, I want to identify then the inverse. If I've made no errors, the right side is my inverse. And that's a big if I've made no errors. We will check this. This was a very generic problem that I just did, and the result is ridiculously commonplace, that I have a matrix of all fractions. That's far more common than not. Okay. I'm pretty sure I did this right. So now all I have to do is take this and multiply it by this, and I'll be done. Or I'm sorry, multiply it by here. I'm pretty sure. Can I be absolutely certain this inverse is correct? Before I continue, I need to know that the inverse is actually correct. I think we all agree there's about 100 places we could have made errors. And how many errors do you have to make to completely mess this up? Only one. How do I know if this is correct?
You multiply it by the original matrix,
And
see if you get the identity back.
perfect. I multiply A by A inverse, and I either get the identity or I don't. But what about all those 38s? Okay, check this out. -11 plus 15, that's 4. Sorry, did I do that right? -11 Oh, I've got a boo-boo already. Something's not right. Did I drop a negative? Oh, that's not an 11. What is that?
13.
That's not an error. I just can't read my own writing. Sorry. There we go. Let's try that again. Negative 11 plus 15. Where does that put us? That's 4. Well, that's even worse. Plus 52. Uh-oh.
Negative 11.
I lost something here. Oh, I'm going the wrong way. That's what I'm doing. Sorry. Ah, that's what. I'm going across. So I have negative 11 plus 9 plus 40. Negative 11 plus 9 plus 40 is 38. 38s. Did you catch that? I only multiplied the numerators. That's why I want all my denominators to be the same. Because then all I have to do is add up the numerators. And guess what I have to get? Every numerator is a 38 or it's a 0. Anything else will be an error. I know, it's hard to do this way. So I got negative 11 plus 9 plus 40, that's 38 over 38. Now, this guy. So I have negative 5, negative 27, that's negative 32, plus 32. It's a good start. By the way, just because the first few work doesn't mean it's right. I could have an error somewhere else, and I won't know. I literally won't know until I do all 9. You can't stop prematurely because there could be an error and you'd never find it. Okay, so 13 minus 21 plus 8, that's 0. Now, second row, first column. 22 minus 12 minus 10, that's definitely 0. Over 38, if you will. Now we're the middle. 10 plus 36, that's 46. Minus 8, that's 38. Over 38. Negative 26 plus 28 minus 2, that's definitely 0. All right, negative 33 plus 3 plus 30, that's 0. Negative 15, negative 9 plus 24, that's 0. Little drum roll, please. 39 minus 7 plus 6. Crowd goes wild, confetti everywhere, dancing in the streets. Or is it more of a, we didn't screw it up? Yeah, it's probably more of a, it's supposed to work. The opportunity for error is all over the place. You're gonna make mistakes, just, deal with it. Try to minimize them, and as you go, try to eliminate them because you get more efficient. And I'm not joking. Did anybody do this quiz perfectly on your first try? If you raise your hand, I know you're lying. Because you made mistakes all over the place and you fixed them, hopefully. But what will happen is the mistakes get fewer and far between because you just become better at looking for the places you make errors. How many at least once dropped a negative sign? Good, most of the hands went up. That's the normal mistake. Did anybody just simply write down the wrong number at some point? That's the next most common error. You will stop doing that because you get tired of redoing the problems. And that's not a joke. You will be so efficient at doing things and proofreading in a few more weeks, and you'll say, when did that happen? Because you got tired of redoing things, but you'll also start looking for the places that you know you might make a mistake ahead of time, and then you just won't make it. I have absolute certainty that I have the right inverse now. If I don't do this check, by the way, I never need to see this check. I always absolutely assume you did it, because if you didn't do it and A inverse is wrong, then no part of my final answer will be correct, and I'll never be able to fix it because I won't know where the error is. So now that I've got that, I can say that my solution is A inverse times B. So now I am going to write these side by side. I know I have to write it one more time, but it's easier. Well, actually, you know what? I'm going to be lazy. I'm going to be lazy. I don't want to write it again. There. How about if I just do this? All right. There, I'm being lazy. A inverse times B is this. This is also my solution. So what I get should be a column vector that is x1, x2, x3. So let's do this product. Negative 77, negative 15, that's negative 92, plus 130, that's positive 38, over 38. Negative 21 plus 27, that's 6, plus 70, that's 76, over 38. I'm sorry, 70 plus 24, that's 94, plus 20, that's 114, over 38. You were expecting something ugly, weren't you? Happy solutions usually still come from ugly inverses. Is finding the inverse a more efficient route than just simply doing the row operations, Gaussian elimination in this case? Oh, no, it's not. If I wanted to use a calculator, is it more efficient? Significantly more efficient. Yeah. Oh. Because technology is going to do, we're going to do everything a little bit different, because things that are slow for you aren't fast, or excuse me, aren't slow using technology. There are a lot more steps, but the technology can do them at light speed. Now, in this case here, finding the inverse, you said, but Mr. Run, you said when you find an inverse and you've got all these fractions, and technology often gives you decimal approximations. But I'm going to show you a way to do this where, even though it's all fractions, you don't have any fractions in your answer until the end. Technically, in a sense, can I think of this matrix as 1 over 38 times a matrix of integers? And didn't I basically just do the problem that way when I multiplied and checked? So what if I could show you a way to come up with the matrix of integers where the 1 over 38 was separate from the problem? That matrix of integers might be really fast to come up with. I can show you how to do this problem faster than you can do using row operations. That's the end of chapter 3. That's an application problem. And that's exactly the way technology is programmed to do the problem. Technology is no longer programmed to do the problem the way you would do it by hand using row operations, because of the problem with row operations. Pivots have to be a 1. What if my pivot was a 38? Then that means all my decimal value, I'd have all decimal values. And what if my inverses, if I saw a matrix of decimals, would I feel comfortable with that? No, because now you have terminating decimals. So when I multiplied, would I get integer values? No, that would be impossible. We'd get decimals. Close, but they'd be all decimals. And for generations, this is how all technology gave you answers. It gave you answers that were really, well, close. But I have integer solutions. I don't want close, I want these. So everything we did was true, was valid. By hand, no, that's not efficient. Doing row operations would have been better, but I'm going to show you the link between what we do by hand and what we use technology, and how the technology does it. So I can do this problem using technology by finding the inverse first and doing it that way, but finding the inverse void of the fractions. That's a completely separate way of looking at the problem. That's what we're going to do at the end of chapter 3 when we look at those applications. Cool stuff. In fact, that's the last lecture of material that is on the first test. That's 4 lectures from now. It's not that far in the future. Very cool stuff. So, big picture, why do I need an inverse? Well, it's a way of solving a system. It's not the only thing we use it for, but it is a way of solving a system of equations. We will use inverses all throughout this course for various reasons. So what I want to do is to be able to find it efficiently. You're going to learn an alternate method to calculate an inverse. It's not better, it's just different. And for 3 by 3, you'll find that the 2 methods are about the same amount of work. Bigger than 3 by 3, this is by far faster by hand. Bigger than 3 by 3, the other method is far faster using technology, which is why you need both. Because remember we talked about the Sacramento downtown grid? What if there was a unique solution to that problem? What if there was? You've got a 20 by 20 matrix. 400 entries into a matrix. I had to do I had to do 9 separate calculations here. I really don't want to do 400. It'd be nice to be able to do this using a computer, but if all my denominators were astronomically large numbers, perhaps I could be in trouble. But what if I could do it with only integers and keeping the bad fraction outside? And don't lose anything. That's what we're going to learn how to do. So that's why it's so necessary that you understand the computer application, even though you're never going to use it physically in this class, because we're going to do small enough problems. You have to understand the computer application, because that's how the big problems are done, but you also have to understand what tweakages we've made over the years to ensure that the computer application actually gives us the correct answers. You see, the biggest nemesis for the computer application is fractions. Computers don't store fractions. But what if I could show you how to store a numerator and store a denominator? Anybody got any coding skill in this class? What if I stored the numerator almost like a word, and I stored the denominator as a word, and then I presented my answer word divided by word? I mean, it sounds kind of silly, but in a sense, that's kind of what we're doing. We're treating it as 3 over 38, we're treating it as a 3, and then I'm putting it over 38. I'm not going to actually do a decimal calculation. I'm going to present that almost as if it's a text, because I'm giving you the answer. I don't want a decimal, I want the exact value, because I'd never be able to work backwards. You're not going to get this if there's a single decimal. So there's some really cool stuff along the way. This is how you find an inverse. Okay, let's do a smaller problem now. Do a little bit smaller. Okay, I've got 13x minus 47y equals 106, and I've got negative 19x plus 21y equals negative 37. All right, I want to solve this problem. We're in baby algebra, we have 3 ways. Graphing, substitution, addition. Graphing, don't think we'd have any success there, do you? Yeah, all icky fractions. I can do this using the addition method. That's where I take multiples of one, add it to multiples of the other to cancel, and I can do that, no problem. I can do substitution. That's where I solve for one variable. What if we do this using an inverse? Let's try doing an inverse. So the first thing we're going to do is we're going to write this as a system, we're going to write the system as a matrix product. So we've written it in the form AX equals B. Now let's calculate by the way, I'm not asking you for the inverse. If I asked you for the inverse, this is the matrix I want to see. I don't want to see a 1 over 38 times the matrix, because it means we're not done. I still need to multiply the 1 over 38 in. I'm asking you to solve this problem. I'm not asking you for the inverse, I'm asking you to solve this problem. It's not the same question, is it? We're going to use an inverse, but I don't want to multiply the fraction in, because then I'm going to have to deal with fractions. So what is A inverse? Well, let's see. Do you remember what to do with the numbers? Swap those, change the sign on those, and what goes here? I need a calculator. So 21 times 13 minus negative 47 times negative 19, and that's really next, negative 620. Now, if I want the inverse and that's the end of the problem, then I do this. And this is absolutely correct. If this was the ultimate goal in the problem, I wanted to solve this system using the inverse. So can I use these numbers and then multiply this in last? Well, that's essentially what I was doing over here. You didn't realize that's what I was doing. Wasn't I only using the numerators, then doing the denominator? Which, by the way, if I wrote this, I'd do the same thing. I'd only use the numerators and then do the denominator last. So my solution, x comma y, or I should say xy, is this 106, negative 37. But if we're wise, we will ignore the denominators until the end. Okay, in other words, literally treat it like this problem. All right, so let's do this. So I've got negative 21 times 106 minus 47. So I've got negative 3965 over 620. Can I reduce that? Yeah, I'm not going to reduce it yet though. And then here I'm going to have negative 19. Looks like here I have negative 2495 over 620. Does anyone else get that? Do something different. Did I make a boo-boo? So all of these should be negative because that was negative. What did you get, Monty?
I got negative 487 for the first one. But my matrices are the same, maybe I made a mistake.
No, I think 487 is right in the first one.
Did I lose a sign? Let me do this again. I may have lost a sign. The answer should be. Let's see. Well, what's bigger? Let's do that. Negative 21 times 106. I'll give you a hint. It has to be a big negative number because it's a negative number minus a positive number. Minus 47 times 37.
No, your top one's correct. You get negative 487 if you do 21 times 106 minus or plus 40 negative 47.
But you shouldn't be adding. You should be subtracting.
So yeah.
Oh.
Negative 339.
Did you add or? Oh, I subtracted, didn't I? Ah. Yeah, that's. So that okay, that makes sense. I'm looking at this going, okay, negative 2. Let me try this one more time. I think I dropped a negative somewhere. Plus, there we go. Oh boy. Yeah, negative 487 is correct. Yeah, I just simply dropped, I said they're all negatives and I wrote it, I dropped one of my negatives. Now, how about here? That's probably not correct either. Now, let me check. Negative 19 times 106 plus 13 times 37. Yeah, I did the same thing. I dropped, I think I dropped the negative. On both times, I think I dropped the negative on that one. My bad. Okay, do these reduce? Maybe. They may reduce, but if they don't reduce to the same denominator, then is there an advantage reducing them? Not really. It's, by the way, it's totally correct to reduce them if they reduce. I suspect they probably don't. Well, how do I know? This is one of my favorite features. I'm going to go 487 over 620, and my calculator gave me back 487 over 620, which means it doesn't reduce. So you don't have to force it. So it appears that my solution is this. Here was the point. I made about as ugly a problem as I could make for two variables. Do you agree? Without fractional coefficients. We could have done any algebraic technique that we know, and it would have been slow because of all the icky fractions. But what we did in such a way that technically we never dealt with a single fraction anywhere in the problem. In other words, I said literally you're ignoring the denominators, you're only putting them into the answer. That's what I did. I never used the 620 anywhere, I just threw it in my answer. And that actually made this problem really fast, didn't it? Now, you literally could have left it in this form and then did this at the end. It doesn't make any difference. I probably should have done that and lost some negatives. But this is another way of doing the problem. Could I have done this problem using row operations in a matrix? Sure. But the lack of a good pivot means I would have been dealing with horrible fractions. I don't think I want to do that problem using a matrix. The numbers are just far too unfriendly. So we have an alternate way of doing it. That's very cool. All right, now we're going to change gears. We're going to get a little theoretical on you. Okay? I want to program a computer to do row operations. Now, this is not a trivial thing. A computer, I need to do a calculation on something. How do I do a row operation? If you think about this, how do I tell the computer to take rows and add them to other rows? What if I told you every row operation can be performed as a matrix multiplication? In other words, the computer can't do a row operation. That's actually impossible. But if I show you that every row operation is simply a matrix multiplication, then when I want to do row operations, I tell the computer how to do the matrix multiplication that performs the row operation for me. Does that make sense? Yeah, a computer can't do a row operation. That means I'm taking apart and strategizing. No, I don't need it to. I just need it to get the result of my row operation. So we're going to introduce something called elementary matrices. Now, this is very theoretical and not entirely practical for what we're doing. It's more of a computer application practicality down the road. Now, here's the idea. There are exactly 3 legal matrix operations. Row switch, multiply a row by a scalar, or use a multiple of a pivot to add another row. I can't add through multiple rows at one time. 3 of these plus 5 of these is not a legal row operation because there's no one step that could get me there or one step that could get me back. You cannot use a pivot and simultaneously act on a pivot at the same time. By the way, the ultimate illegal act that makes matrix problems so much easier. I have the following matrix. I have a 1, a -1, a 1. So I'm going to use my pivot here, right, to put a 0 here and then put a 0 there, and then I'm going to add this one to here to put a 0 here. Do I see people do this? All the time. I will see this on a multiple. Now, what's wrong with that? That means that every matrix that exists, you will make into the 0 matrix, won't you? If I can use a pivot and act on a pivot, then I will end up with a column of zeros on every problem that exists. Well, that'll make my life easier if I just make everything zeros. Or will I lose all the information and, no, it actually makes it impossible. You cannot use a pivot and change a pivot in the same step. That's the ultimate illegal act. And it wouldn't matter if you got the right answer because actually if you got the right answer, it probably means you had to make a whole bunch of errors. It would be impossible to change the pivot and use the pivot and get the right answer because you've completely changed the entire nature of the problem. It's no longer even a similar question. Because if it's legal to change the pivot, then all pivots would end up being 0 before you went on to the next step. Ooh. But if I do legal row operations, that means take a multiple of the pivot to add to another row. You're not changing the pivot, you're changing the other row. That's a legal row operation. When we're doing matrix algebra, we often perform more than one row operation at a time because it's efficient. But what if I said, let's break it down to just one row operation at a time, and then we're going to analyze, because I want the computer to do this for me at some point. Why? I have a really, really big problem. I don't want to do it by hand. But you're not going to program the computer. You have to understand the person who programmed the computer to do this, how did they do this? It wasn't that long ago. I was teaching at Mesa College when no calculator built would give you a right answer to a matrix question. And if it was right, it was just luck. You overly simplified the problem with lots of 1s and lots of 0s in your coefficient matrix, so you couldn't get any decimals. No, if I asked people to do it using a matrix, I got the wrong answer basically 100% of the time because the technology, people didn't know how to do the programming yet. They fixed almost everything, so it's beautiful, but they don't do it the way you would think they do it. Okay? The way we do things by hand is not the way the technology would do it. But the way the technology do it is not always efficient by hand. That's why I'm showing you everything. So an elementary matrix, here's the idea. I said there's a set of what are called equivalent conditions. Let's start with a matrix product, AX equals B. This will have a unique solution if and only if A is invertible, A is non-singular. A is invertible if and only if it is row equivalent to the identity matrix. It is only equivalent to the identity matrix if A can be written as a product of elementary matrices, which is what we're going to do next. And this is often how the computer is going to do the problem. I'm going to do a really small problem. We're not solving a problem. We're just going to take a really simple matrix. So let's suppose I give you, how about 4, 1, -3, 7. I want to do row operations on this matrix until it looks like the identity matrix. It's a 2 by 2, that means the most number of steps it should take is 4. Sometimes we're really inefficient, we might take more. Wouldn't be wrong, it'd just be not great. So, what would the first step you want to do? Take 1/4 of row 1? Yeah, let's go row switch. So let's change. We're going to go 1, 7, 4, -3. Now, let's use our pivot of 1. So how about I take negative 4 row 1s and I add it to row 2? So 1, 7, 0. Negative 4 of these plus this would be negative 31. Okay. The next step would be I want to take negative 1 over 31 times row 2. And clearly there will be one more step. My 4th step. And that would be to take negative 7 row 2s and add it to row 1. Great. Is there another route legally that you could have done? What? Give me a different first step.
Don't swap them and just use fractions.
Or?
Subtract 4
No, there's no row subtraction. Row subtraction would actually involve 2 completely separate. Row addition, but how about if I added negative
3
row 2 to row 1? Would that have been a legal first step? Oh, so there were 3 completely legal, easy ways to get a 1 in that pivot. Do you agree? But once you did that, would that change the nature of your problem? Would that give you an entirely different set of steps? Yeah, because you'd have different numbers. So if you said take negative 3 row 2s and add it to row 1, I would see a different position for the numbers. It'd still be correct. So the answer we're going to get is not unique, but it will be correct. So the first thing we're going to do is figure out what are the elementary matrices. I'm going to demonstrate to you how this works. It's not something you would have thought of ahead of time that you could do, but it's actually quite simple. Okay. What I'm saying is my very first step in the problem was a row switch. There's a matrix multiplication that does a row switch. So I'm going to label my matrices E1, elementary matrix 1, E2, and I'm going to put them in the margins here, by the way, E3, and E4. Starting with an identity matrix. You're always starting with the identity. If I did a row switch on the identity matrix, what would I see? Let's remind ourselves, what's the identity? That's this one. If I do a row switch on the identity matrix, what matrix will I get? You with me?
Does that have a special name? Or is it just...
So it's called an elementary matrix because I did one step on an identity matrix. Now, starting with an identity matrix, do negative 4 row 1s and add it to row 2. Is that the matrix you'd get?
Yeah.
Starting with this, if I do this to the identity, I would get this. So this is an elementary matrix. It's one step on an identity matrix. All right? Starting with an identity matrix, I want you to do negative 1 over 31 times the second row. Is that right? And starting with an identity matrix, I want you to do negative 7 row 2s plus row 1. I get that. Okay, now to verify that I did everything correctly, I want to do E1 times A. Let's start with E1 times A. Two stray marks here. Okay. 1, 7, 4, negative 3. The row switch that I was asking you to do, we performed by doing this particular row matrix multiplication. Do you see it? I multiplied instead of actually physically doing the row switch. I multiplied by the matrix that would perform the row switch. Now, let's do E2 times E1A. That means I want to take my E2 times this guy right here. 1 plus 0, 7 plus 0, negative 4 plus 4, negative 28 plus negative 3. We did 2 row operations to the original matrix We did two matrix multiplications on the original matrix, and we're at the same place, aren't we? Do you see a trend here? Let's keep going. Now let's do E3 times E2, E1A. Notice I'm going to do it on the result. One, 7, 0, 1. Oh, who knew? That's my third matrix. And then finally, I think you guys all see what's about to happen. Now let's do E4 times that result, which is E3, E2, E1. Matrix multiplication is not commutative, but it is associative because you're not changing the order you do things. So if you had to multiply 3 or more matrices in a row, you just multiply them. Ordered, you can't change the order of the positions, but if I wanted to do this, I literally could say, well, I can do those two, and then those two, and then the result. As long as I'm not changing the order, it's not going to change the answer. So this, obviously, was, what was the last one? It was 1, negative 7, 0, 1 times 1, 7, 0, 1. 1, 7 minus 7, 0, 1. And what did I just prove? In this problem, I just got, I got A inverse is, not A inverse, I'm sorry, not the identity, sorry. The identity is equal to E4, E4, E3, E2, E1, A. Isn't that interesting? What this means is my original matrix A is row equivalent to the identity because we did row operations. It also means I could do elementary matrix multiplications to get to the same place. Same number of multiplications, right? Same results. I am interested in A inverse. If A is row equivalent to the identity, then A inverse exists. This is one of the equivalent conditions. This is what we did today. That's how we found an inverse. If I can take A and get it down to the identity, then by doing the same steps on the identity, I take it down to A inverse. If I do A inverse and the steps in reverse to get it back to the identity, then the identity would get me back to A. That's why if I do a legal row operation, you can always go in both directions. So here's what I'd like to do. I would like to write A equals. I want to write A equals. Well, that would mean I need to find inverses, don't I? I need to find inverses. Well, there's an order I kind of need to multiply by. I'm going to erase this because I don't need this anymore. All right, so here's what I got. I got identity equals E4, E3, E2, E1, A. What if I multiply both sides on the left by E4 inverse? Matrix multiplication, although not commutative, is associative, which means I can think of it like this. What's E4 inverse times E4? Identity. An elementary matrix means I did a legal row operation on the identity matrix. I can always then undo that legal row operation. So the inverse will always exist. How do you think you undo a row switch?
Switch again.
How do you think you undo multiplying by a scalar?
Multiplied by the inverse of that scalar.
Reciprocal of that scalar.
Oh, sorry.
Yeah. How do you undo adding a multiple of a pivot? The inverse operation would be adding the opposite sign of the pivot. The word inverse was correct, but multiplication and addition would be different inverses. So reciprocal and multiplication, additive identity, I can undo each of those easily. I mean, it'll be trivial. It'll take us 2 seconds, literally. So what do I have on the board now? I now have E4 inverse times the identity matrix. Can I just leave it as E4 inverse? And the right side is then E3, E2, E1A. So now let's multiply both sides on the left by E3 inverse. Can I skip a couple steps? Do you see where this is going? What am I going to do next? E2 inverse. E1 inverse. In the end, what does matrix A equal? Because I'm going E2 inverse, E1 inverse. If a matrix is invertible, then it is row equivalent to the identity matrix, which means it can always be written as a product of elementary matrices. And that's what we're about to do next. We're going to write A as a product of 4 elementary matrices, but these aren't the ones that I figured out. I figured out E1 through E4. How the heck do I find the inverse? Well, that's actually easier than what we just did. I don't want to go much lower than this, folks in the back. How do you undo a row switch? With a row switch. Oops. How do I know? Because when I multiply these, I'll get the identity. And that makes it really easy. How do I undo? How do I undo adding -4 multiples of row 1 to row 2? Add +4 multiples of row 1 to row 2. When you multiply these two out, you will get the identity. You notice I don't have to go through and calculate the inverse like we did before. If you start with an identity and you do one step, just undo that step. I didn't have to create a situation to figure this out. Have you not your multiply? 1, 0, 0, 1. Okay, E3 inverse. How do I undo multiplying row 2 by -1/31? Multiply row 2 by, not positive, -31. How's that? And again, going quick check. 1, 0, 0, 1. And finally, E4 inverse. How do I undo taking -7 row 2s and adding it to row 1? Taking +7 row 2s and adding it to row 1. Okay? I am claiming that this times this times this times this will give me my original A. I'm going to check it. There's always a chance I could have just, dropped a negative or done something silly. Probably didn't, may have. So I'm also going to show you a very efficient way of doing this. I need to physically perform this. So I'm going to multiply these 4 out. All right. So I do these 2 times all these, and then that times all these. And no. Do these 2. Do these 2. Be lazy. What's this part? What's this part? And then what's this product? If I didn't mess it up, it has to work. Isn't that crazy? Okay, if you didn't get anything else out of this, big picture, every legal row operation, only one at a time, every legal row operation can be performed with the matrix multiplication of an elementary matrix. So when I want the computer to do row operations for my Gaussian elimination, the computer physically can't be taking multiples of one row and adding it to another row. No, the computer's going to perform the matrix multiplication, because that's easy. And I program the computer to perform the matrix multiplication when the pivot looks like this and the other number looks like this. Does that make sense? The program is going to have the steps look exactly like what you would have done by hand. But nobody in their right mind is going to make this a matrix multiplication. You're just going to do row operations. But every row operation can be performed with the appropriate matrix multiplication, and then I can also work backwards. I wrote E inverse, or A inverse is the product of elementary matrices. Where in here did I write A inverse is the product of elementary matrices? Well, it's pretty much right there. E4, E3, E2, E1 multiplied is A inverse. How do I know? Oh, so I can get A or A inverse with elementary matrices. A inverse only exists if A was row equivalent to the identity, meaning I could do the steps, then I can actually write A as the product of elementary matrices, and then A inverse would be the inverse of that product. In reverse order, by the way. Now, I do want you to notice something. Do we agree then that if A is E1 inverse, E2 inverse, E3 inverse, E4 inverse, and A inverse is E4, E3, E2, E1, does this present a problem? No, actually, this is pretty easy to verify. How do I verify this easily? Put them next to each other. Let's multiply them. E1 inverse, E2 inverse, E3 inverse, E4 inverse times E4 times E3 times E2 times E1. Let's use associativity, shall we? Do you see it? There's the identity, okay. Then what am I going to do? And then there's the identity. And then I'm going to do identity, identity. Isn't that cool? Or, here's a way better way. That's perfect. Here's a way better way. Oops, sorry. Let me do this one before. This I did not show you last day, but it's actually a very simple proof. I'm going to prove this one right now because it's huge. I did something with the transpose last day. I said when I take the transpose of a product, when it's legal, then it's the product of the transposes in reverse order. This is a very simple proof I'm going to do right now. This is critical. You will use this often. Okay? Suppose A and B, A times B equals the identity matrix. Okay, what does that mean? That means they're inverses of each other. They're both n by n, they're inverses. Oops. I'm going to prove to you, remember, A inverse A and B inverse exist. A and B are both square matrices, their inverses exist, and their product is the identity. But in general, or actually, you know what? I'm not even going to say that. I'm going to change that. Let's just suppose A inverse and B inverse exist. How's that? And they're both n by n matrices. They're not inverses of each other. I'm going to make it more general than that. A and B inverses both exist. I have two n by n matrices, just random. Make up a couple of 2 by 2s that are just random. I'm going to prove this right here without using any identities to start the problem. How do I prove this? Well, what is AB? First of all, what does AB times AB inverse have to equal? Doesn't it have to equal the identity? So, let's take AB and let's multiply it by this quantity instead. Matrix multiplication, although not commutative, it is associative. So can I write it this way? You see it? There it is. You start with two invertible matrices that are the same size. The inverses had to exist to begin with. Then if I want the inverse of the product, it is absolutely always the product of the inverses in reverse order. So what is this? Oh, that's why all of them got in reverse. Did anybody wonder why in one way it was 4, 3, 2, 1, the other way it was 1, 2, 3, 4? Because the inverse of a product is the product of the inverses in the reverse order every time. Not because I said so, we actually got it when we did it, and then I'm proving it over there in general. So if I wanted to take the inverse of this product, it'd be 4, 3, 2, 1 without the inverses. The inverse of this product is 1, 2, 3, 4 inverses. The one common mistake people will make is they'll forget to switch the order. And then it won't work and you won't know why. Okay? So inverses, powerful things. Elementary matrices, powerful things. Yeah, second.
For elementary matrices, you said that they are one row operation.
Take the identity matrix and perform exactly one row operation.
But the thing is, you said computers don't know how to do row operations. So
No,
how
no,
do they?
as a row operation, so what you
Yeah.
want to do when you have a system, you want to program, it's already been done, just so you know. But let's go back to generation 2 when it hadn't been done yet. And people couldn't figure out why they're getting wrong answers left and right. So I want to make my pivot 1. That's the first thing. The computer has to have the pivot of 1. So you basically, what the computer always does is multiply by the reciprocal of that first guy. But what if there's a 1 along the way? You'd rather the computer did a row switch. Or if let's you have a row of all even numbers, you know, maybe there's things you can do, say if this, then this. If you've written code, you guys understand. You know, if then loops, you know, do loops, if then else. Let's keep it simple. So I get my pivot of 1. But I can only do 1 pivot at a time because it's 1 multiplication. Remember, the computer's fast. That's not a problem because it's going to do it in a fraction of a second. So I make the pivot of 1 by either doing a row switch or doing something that gets me a pivot of 1. Now I do that however many times it takes to do that. So there's a pivot of 1, I want to add this multiple, then I tell the computer to do this particular matrix multiplication. If the number below is k, then do this particular multiplication. Exactly. Does that make sense? It's not that hard.
The question I was going to ask
Yeah.
is, did someone have to program every individual elementary matrix for any operation you'd want to do?
Well, but there's only 3 forms: row switch, scalar multiple, pivot.
So can you put like a variable, and then you just tell the computer what that
Yeah.
variable is? Is that how it?
Whatever it is, and then whatever this number is.
So are these like double arrays, and you have to like iterate through their?
I'm sorry, the louder.
If you're programming this, is each matrix like a double array, for example, and you have to iterate through the array to make modifications? So like,
There will be a lot of, if I want, let's suppose I start with a problem where the numbers are really, really random all over the place. There's a lot of if then else's, okay? But you can all see that that's really not, that's not the stopping point. It's when I get to a certain place, having to do the right thing is if it's going to require a row switch versus a scalar multiple versus using a pivot, I can tell it to do that as a matrix multiplication. That's if I want to do row operations. Because what if you want that reduced row echelon form at the end of the problem? You're not doing that using an inverse. You're doing that with the row operations. So I want to tell the computer how I want my row operations performed as elementary matrix multiplications. It's just not that complicated. Way back in the day, I used to teach programming. We actually had a fairly strong programming department here. We gave all those classes to City many years ago. I used to teach Turbo Pascal, which is sort of a dead language now, but there were many languages that spread up. All the C languages came from that in the Delphi's. Because Pascal was one of these languages, you could write programs that literally acted like a computer calculator. And so what I would do in this class where there was literally no math background, you'll by the way, when next lecture you'll understand the math because we're going to do it. I would teach them how to do lines of best fit. You guys ever do linear regression? Bunch of data points, here's the line of best fit. Stats. We're going to do it here and you realize it's all matrix multiplication. In stats you had a bunch of formulas that you mindlessly plug numbers in. They all come from what we're doing next day. They're all matrix multiplications. So I taught people how to do it, how to program the computer to multiply the matrices, how to do the determinant, because they're only going to be 2 by 2s. You have 1,000 data points, it's still only going to be a 2 by 2 matrix. And I showed people how to do it, and then in the end you could input as many data points as you want, click, and it gave you the line of best fit. People were like blown away because I showed them how to do the matrix stuff by writing simple code. It wasn't that complicated. But the idea of linear regression when I have an unlimited number of data points and giving me the perfect only answer you could get, wow. It was something as simple as showing people how to do a matrix, how to enter a matrix, how to calculate the determinant, and you need an inverse matrix, and how to multiply the matrices. But once I showed them how to do that, it was a very simple algorithm that was written. This is all based on algorithms. This is not a computer programming class, but a lot of you are computer guys or gals or whizzes, or you're the ultimate computer nerd and you'd like to know, yeah, how does somebody do it? You could probably look it up the details. I don't want to get into coding. That's not what this is about. I'm just saying that it wasn't that long ago that technology really struggled with matrix problems, and people figured out backdoor ways. Now, this has been around for a couple hundred years, but we figured out how to use it. A lot of the old math that's been around forever, we're now figuring out how to use it in technology. Anyway, I need to move on to the last piece of the puzzle. The last piece of the puzzle involves something called a stochastic matrix. Now, stochastic is a very special word. And what stochastic means, first of all, think of everything as percentages. So if I said, let's keep it simple, you're going to do a budget next month and you're figuring out all your expenditures and what percentage of your income. When you add up those percentages, it probably should add up to what?
100.
Yeah, 100%. It probably wouldn't be good if it exceeded 100% or something. Because you're saying, here's how I spent my money, it kind of has to add up to 1. Does that make sense? So a stochastic matrix is one where every column adds up to 1, because it's basically where things were accounted for. Let me keep it really loose. Now, in the textbook, okay, I'm going to refer to the picture because we're going to come back to this, and it's going to be one of the most important problems in the entire course. And section 2.5, I call it the cable company problem. Okay? Let's see, hold on. I don't know. I understand some of these dot cameras aren't really good. Let me see if I can get this one to work. A lot of these rooms, people have just given up on the dot cams. This one looks newer, because not everybody here has a book. The problem basically, it's an overly simplified problem that's a really huge problem in the end. It deals with something we're referring to as steady state. I want to perform the same process over and over and over and over again with the same percentages of here's where everybody goes kind of thing. And in the end, we should be approaching steady state, meaning we're approaching a fixed nature that's independent of the starting point. That's the crazy part. So, did anything happen? Like I said, this thing, I can't tell it's even on. Well, that part's on. I just wanted to save you some time and trouble by just showing you the picture so I don't have to write everything out. Well, something's blinking. I'm getting that. Starting up, please wait. Okay, so let me explain the problem to you. You have two competing cable companies in a particular region. They give you, here it is. They give you the population totals, which really aren't even important. Well, that's not bad. Can you guys see this clearly?
Yep.
Okay, so you have two competing cable companies, all right? And then you have the people who live in the shotgun shack. No electricity, no all the money stuffed under the mattress. In other words, no cable folk. Every year, a fixed percentage of people leave one and go to the other. This is what makes this work, is the percentages are going to stay the same. Is that artificial? Yeah, but it's a big picture problem. So cable company A, in other words, retains 70% of their people. 10% decide to cut the cord. 20% switch to B. Okay? B, 80% stay, 5% cut the cord, 15 go to A, and the Shotgun Shack folks, 70% year in, year out. They don't pay cable bill. They just pirate everything. And then 15% here. Okay, if this kept up year in and year out, we would eventually reach what's called steady state. And so what happens is there's something called a transition matrix. So this makes it really easy. From A to, I would rather put these on the left side, by the way. 70% go from A to A, 20% go from A to B, 10% go from A to no cable. Those are the given numbers. These have to add up to 1 because that's everybody from cable company A. What happened to them next year? So does that make sense? So this is called the transition matrix. Now if I give you the initial distribution of the population, in this problem it says, let's start with, there's 100,000 people in the city. Well then I know exactly, and I'm sorry, 15,000 have A, 20,000 have B, and the other 65,000 are no cable at all. But what's going to happen is every year the distribution is going to change a little based on this. And here's the crazy part about steady state. It doesn't matter I could have all 100,000 people with A. I could have all 100,000 people with no cable. Steady state's going to be the same. You'll just reach it sooner if your starting distribution is closer to the steady state. Does that make some sense? So as we move on, let me see. So down here it shows, here's what you're going to do. It's not the numbers, but it says 100,000 people in the population. So in other words, 15% were with A, 20% were with B, and 65% were with no cable. Now when I multiply the transition matrix by that, it's going to give me next year's distribution. Think of this as 23,000, 28,000, 48,000 if you want to do it that way. Now, what's year 2? I take this and I multiply it by this. And then year 3, year 4, year 5, and so on. But here's the cool part about the mathematics. Can I do this with a calculator? Yeah, but that's not how you do it. So the initial population, or the initial distribution, let's call x0. So x1 equals p times x0. Right? So after I'm starting with x0, after 1 year, this is what we're going to have. What's x2? It's p times x1, which is p times x0, or p squared times x0. Save some time. What's x 1000? P to the 1000th times x0. If you have a calculator that can do matrix multiplication, you can square a matrix rather easily. You can raise a matrix to an exponent rather easily. It's actually fairly trivial. You with me on that? So, when do I reach steady state? This is very similar to Newton's method in Calc 1. Newton's method was a repeated bunch of iterations that you rounded specifically to a certain decimal place. And when you got the same iteration twice in a row, it meant you were going to get that number forever. And that was your final answer. So when xn plus 1 equals xn, you've reached steady state. There's no more changes. Problem is, will that ever actually happen? No, it's a limit as n goes to infinity. Why? Because every time you multiply these decimals, what's going to happen? You get more decimal places. Now, because this represents people, can I round my distribution to the nearest number of people? Yes, because people can't be subdivided. So in that sense, I could reach it in a finite amount of time. But steady state actually technically is a limit, right? P to the n, x naught, it's a limit as n goes to infinity. That's how you get it. But in general, this process is not really fast. So in the textbook, he says, well, let's look at x3. Sorry, let's look at x3. And let's look at x10. Now let's look at x15. And what you see is the numbers are changing less rapidly over time. Maybe you do it the 50th time, the 100th time. Now remember, that wasn't that long ago. People didn't have calculators that could raise a matrix to a power. So how did you do this problem? By hand. But you did a problem with decimals by hand. Now, I'm going to give you the simple, and this is why I have fun with this. Steady state can be reached as I take a limit. We're 1,000 years away from any computer being able to do this problem correctly. You know why? It's called storage. How many decimals can a computer store? Well, of course, infinitely many, right? No. Finite. It doesn't take very long before you would reach the capacity that any computer that will ever be built. Well, in 1,000 years, it's still going to be finite. But your decimal places are approaching infinite in length without repeating. So if I'm doing this problem 100 times, I have a 200 decimal place number. Do you think any computer stores 200 decimal places? No, that's a waste of computer storage. I have a 3 by 3 matrix. By the way, this could be a 1,000 by 1,000 matrix. I have a 3 by 3 matrix where every position is stored in 200 decimal places. You realize what kind of storage and memory I would need to do that? It would be a waste of time. No, I mean, your most powerful computer might store 8 or 10 or 12, I don't know, not 200, not 2,000. What if I need 100,000 decimals? So the problem in general is you can't do this practically. You can do it in theory. You can't do it practically because the decimal storage will fail you. So we're going to do problems later on where I'm going to show you that has nothing to do with the decimal storage. We're going to come back and do this problem at the end of the course. And we're going to start the problem by calculating the steady state. There's not going to be a single matrix multiplication. This is trial and error to give you insight of, hey, this is kind of a cool problem. But you realize that every year the new distribution was different. It was less different than the year before, but it was nonetheless different. So in real life, I think this is one of the most important applications of linear, because in real life we have this sort of thing. It's something from branch mathematics called a Markov chain. An easy way to think about it, you're at a 4-year school, freshman, sophomore, junior, senior. What have we noticed every year? The percentage of freshmen that return for sophomore year is pretty much the same. And then every year sophomores returning to juniors. Do you think pre-pandemic that was a reasonable thing in most schools? Yeah, in fact, that's how all schools plan, by the way. That's why freshman classes typically are much bigger than senior classes. Why? Attrition. But then that has everything to do with them accepting new students and so on. So they can do this type of problem and say, this is the steady state we've reached. Every year it seems that 32% of our campus are freshmen. Maybe 15% of our campus are seniors, whatever. But then they can use this in their planning purposes because they see year in and year out they reach the same thing. What if they started with way more freshmen? Well, things still kind of level out. So steady state is the concept that I have the same thing from that point on. That's the whole idea of steady state. I'm going to show you there's a way mathematically to start the problem and calculate steady state as the entire problem. There is no trial and error, there is no limit, because technically this is a limit as n goes to infinity. But you see, with people, that's not so bad because people have to be integer values. Okay, let's change it from people to water. This is just water flowing. And so I have quantities of water. Oh, those don't have to be integers, do they? Those are measurements. Those technically can have an infinite number of decimals. What if it's electrical current? Oh, yeah. That's why when we did the network problem, we did it with cars. Because now there would actually be a finite number of solutions. If we did it with electricity, which if you look in the book, he also has electrical currents, now there's an infinite number of solutions. Harder to conceptualize that problem, okay? Now, I'm giving you a glimpse. You're not going to do this problem. We're going to do this the third to last lecture of the semester. And it's going to be very cool when we get there, that you're going to be able to calculate this. But this is the whole point of the course, to be able to do the type of mathematics that would allow us to do this type of problem. You've never seen anything like it, nor will you until late in the course. And then when we get there, it's the power of linear algebra in terms of application. Can we go ahead and stop there?